We're good? All right. So, up until now, we've talked about limit problems and how to solve limits graphically, tably, or the tables, numerically is the proper way. And yesterday we said analytically, which was basically with algebra. The way we did it with algebra was we looked at the limit laws, and then we said, hey, for some of these functions, we can find the limit by just the direct substitution. It's not a problem, okay? But there are some types of functions where you can't do that, okay? And that's what we're going to be looking at today. So this is, I think, 1D, solving limits analytically, but the hard ones. So maybe limits analytically advanced, if you want to, level 2. Just as a reminder, x squared plus 3. Just, I feel like I didn't specifically say this with limits, but it might be kind of helpful. Anytime that you have a function, you can talk about the x values of the function and the y values of the function, okay? So, Roger, you and I were having a conversation the other day, and this, as I was reflecting on that, this made me kind of think of it. When we are looking at this part of the limit statement right there, we're talking about the x values. As the x values are getting closer to here, okay? So 1, 2, 3, 4, 5. And then this part up here is talking about the y values. And so, or how those y values are associated with it, that's the function rule. So the whole limit statement is asking, what are the y values approaching as the x values are approaching here? Does that make sense? So in this case, what are the y values approaching the up and down values as x is getting closer to 5 from the left and from the right? So you could say that whole limit thing is asking what are the y values approaching? That's not anything new, but that's maybe a different way of saying it, is to think of it. This whole question is asking, where are the y's going, where are they trending, as the x's are trending towards this? So, slightly different way of thinking about it, but I thought that might be helpful looking back and looking ahead. So, solving limits analytically. Let me give you a brand new problem here. The limit of x squared plus x minus 20 over x minus 4 as x approaches 4. Now obviously we could, if we wanted to, we could graph this. I'm going to hold that away from you right now. We could use a table also, not allowed at this point. So you say, all right, then the only other tool, Mr. Goddard, is the direct substitution method. So let's go ahead and try the direct substitution method. 4 squared plus 4 minus 20 all over 4 minus 4. 4 squared is 16 plus 4 is 20 minus 20 gives me 0 in the numerator. And 4 minus 4 is 0 in the denominator. The 0 in the numerator, that's no big deal. We can handle that. Any 0 divided by whatever would be 0. However, the 0 in the denominator gives us lots of problems because division by 0 is not defined in mathematics. So the direct substitution method sort of fails us in this case at this particular limit location as x approaches 4. So you might say, well, forget direct substitution or forget algebra and analytically, we're going to have to go to the graph. And I say, well, just wait 1 second. We might be able to manipulate this and change it a little bit and then be able to do something with it, all right, and then be able to find the limit, okay? And that's what we're going to do today. We are going to manipulate this expression right here, okay? Ivan, any ideas how we can manipulate maybe the numerator?
Factor it.
Let's factor it.
X plus 5, x minus 4.
X plus 5 and x minus 4. I'll put that denominator in parentheses, and now you say, aha, x plus 5, x minus 4 is canceled, so this limit, or rather that function right there, is almost identical to this right here, x plus 5. As x approaches 4. So what we can do is we can basically transition this equation down into something that looks like this. Now let's try direct substitution. Oh, 4 plus 5, that's not too bad, that's just 9. No, look, Ma, no tables, no graphs. It's right there, the answer's 9. Now, the question is that right? Because x plus 5 looks a whole lot different than x squared plus x minus 20 over x minus 4, doesn't it?
Mm-hmm.
Yeah, it does. But does it really? I mean, symbolically, this one's got a whole bunch, it's got polynomial and division and stuff like that. But what does the graph look like? I'll tell you what it looks like. This one up here, x plus 5, we know what that one looks like. It's a line, goes through 5 as y-intercept, and has a slope of 1. So that's what x plus 5 looks like. You know what this rational function looks like? X squared plus x minus 20 over x minus 4? Looks exactly the same. Graph it on your calculator. Graph that one right there. X squared plus x minus 20 all over x minus 4. Use your parentheses. Yep. Do you see the graph? Do you see the hole? Yeah, you're not. It's not gonna. Let me see that real quick. Here's what it looks like, Gracie. Hold on. All right, hold on. I can hit the y equals sign. Look at that, some crazy rational function. There we go. Total number of views, 1. While he's fighting that battle, we'll just say, so that's x squared plus x minus 20 all over x minus 4. Okay? Your calculator's not going to be, it's not going to have the wherewithal to know that it needs to put a circle right there. There is a hole right there, but it's not going to show it to you because unless you zoom in really far. Okay. Anyway, so yeah, and if we were to look at those graphs, we would say, duh, as this function is moving along here and the x value is getting closer to 4, this is approaching the same thing from both sides. And it's the same exact thing as this one's approaching. The only difference is that this function right here, when you try that direct substitution, when you try to plug in 4, you get something that doesn't exist because there's a hole in the graph. There's a 0 in the denominator. So we just remove that and we fill it in with what this one is and try the direct substitution. So that's one of the methods that are available to you if you come up and you need to use direct substitution, and that's the factor method. One more factoring problem. X cubed minus 1 over x minus 1. You may see something like this on your homework. You always want to try direct substitution but I think it's pretty obvious. You plug in 1, you're going to have 1 minus 1 over 1 minus 1. That's going to be 0 over 0. It's not going to work. And you might say, I don't know how to factor x cubed minus 1. Well, that's actually the difference of 2 cubed. That's a cubed minus b cubed. You may need to look in your book once we get them later this week, or review online how to factor cubics, but I'll just tell you right now it's going to be x minus 1 times x squared plus x plus 1. It is possible to factor that. We normally know the difference of two squares. A squared minus b squared is a minus b, a plus b. This is another one. A cubed minus b cubed does factor into it's a minus b, and it's a squared plus ab plus b squared. But that's something to look up. And so we really just get the limit as x approaches 1 of x squared plus x plus 1. Using direct substitution, you get 1 squared plus 1 plus 1, and so that's 3. So just another quick example of factoring. As a way of solving these problems without a calculator. All right, any questions? I'll leave that up there for you. James, make sure I'm still in the frame if you don't mind. I'm going to give you another method here. It's called the rationalized method. And you use the rationalized method when you have functions that you're trying to take the limit of, and they have some sort of square root in them. So you start off with direct substitution because you want to. Always give that a shot, and we end up with 0 plus 1 minus 1 all over 0. And it kind of takes you down to dead end, does not exist. So the rationalized method is basically rationalizing the numerator or rationalizing the denominator. And we did stuff like this in pre-cal. It's been a little while, so the trick is, if you have something where there's a square root, you can normally get to some interesting results if you multiply this by the conjugate of the numerator or the denominator. It just depends on what the situation is. So if you have a square root term here, the conjugate would be square root of x plus 1 plus 1 over square root of x plus 1 plus 1. And you might say, why would I ever do such a thing? It's going to make it more complicated. Temporarily, yes, but in the long term, no. The reason why we multiply it by the conjugate, and the conjugate is just the same thing that has the two terms, but with a minus instead of a plus or a plus instead of a minus, is because then you get a situation where you have a minus b times a plus b. Yes?
Do you change all the minuses to pluses?
No, I just change the when I have the term and then another term, then the thing in between the terms, the sign in between the terms, is what I switch. Okay. Notice I did not change the plus inside the square root to a minus. I just changed the big plus or minus. That make sense? And so the reason is, do you see how this fits the pattern, Rigel? A minus b, and now we have just a plus b. And so that if I had changed that plus to a minus, then I'd be fundamentally changing what a was. Okay? I don't want to change what a is. I want to just change the sign in between them. Now, does anybody remember, James, perhaps a minus b times a plus b?
Okay. What? A squared plus 4. A squared plus ab minus b squared.
Close. squared minus b squared.
Yeah.
Those middle two
I forgot.
terms cancel out, because the middle term is going to be a times b, which is ab, and then you have a minus b times a, that's a minus b, so those cancel out. So you're just left with an a squared minus b squared. So what this is going to be is this first term squared, so the square root of x plus 1 squared minus the other term, which is 1 squared. All over. Fractional multiplication means denominators get multiplied, so x times, and I'm going to leave this whole thing in parentheses, square root x plus 1 plus 1. If you notice here, I have a square root quantity squared. Alright? And so square and square root cancel each other out, and you end up with just an x plus 1 minus 1 all over x times quantity x plus 1 plus 1. The nice thing about that is the plus 1 and the minus 1 cancel each other out. So I have x in the numerator, and the denominator I have x times the quantity x plus 1, or squared x plus 1 plus 1. You can see now I have a term in the numerator, and I have x times all of that in the denominator. So those x's cancel out. It leaves me with a 1 in the numerator, so I have 1 over square root x plus 1 plus 1. So fundamentally, this expression right here is equivalent mathematically to that sucker over there. So instead of writing limit of all of that as x approaches 0, I'm going to write the limit of all of this as x approaches 0. So just sort of manipulate it a little bit. And now we try the direct substitution. 1 over square root 0 plus 1 plus 1. So that's 1 over 1 plus 1, so that's equal to 1 over 2. So direct substitution does work, but I've got to manipulate my function here. The example that I've just done here has the square root in the numerator. You could have the same sort of thing with the square root would be in the denominator, but your process would be the same. You would still multiply it by the conjugate over the conjugate. Okay? Right now, I feel like it would be good for us just to do a short example of what the conjugate would be. What if I had x plus 2 over 5 minus the square root of x minus 3? Okay? Just for some, if that was the case, what would my conjugate be, Rigel?
5 minus square root of x minus 3.
Close. 5 plus
Oh, 5 plus.
square root x minus 3. And unfortunately, you can't just multiply. If I have this and I want to get something equivalent, I can't just multiply it by that. That's going to change the value. But if I multiply it by the same thing over itself, remember, anything divided by itself is 1, and multiplying anything by 1 is the same value, but it just will change the appearance. So that's what the conjugate will be here. We're not going to continue this through. I just want to make sure you see how that is, because it's an a minus b, and this is an a plus b. And so since we said the solution then would be an a squared minus b squared, you don't have to FOIL all this out. You can immediately go to the next step and say, all right, it's going to the denominator is going to be a squared, so 5 squared, which is 25, minus b squared. b is this thing right here, not with the plus or minus part, but just that term right there, square root of x minus 3. So if you take the square root of x minus 3 and you square it, you just get x minus 3. Now, I am going to put that in parentheses because it's that whole term, and that minus sign is in front of it. So you want to make, that's an area where students can normally make a mistake, is they just put x minus 3 and they think that minus just refers to the x, but it's actually referring to that entire term. Okay? I do more of these, but I feel like we get the idea. All right? So that's the second way, is the rationalized method. All right? As a little side note, there are, well, I'm going to put that at the very end. Ooh, actually, we're pretty much at the very end. So, there are some special trig limits. There is another method, but I haven't shown it to you, but I don't have an example of it, but the homework has it, so we'll just do one of the homework problems. So the other method is when you're dealing with complex fractions and piecewise functions, and we'll deal with those for homework stuff. So, there are two special trig limits. And these are the type of things that you'll need to have memorized. Now, I've got a list of stuff that you have to have memorized, and I'll give that to you probably next week. Well, I mean, it's not like I'm going to let you use your notes on the tests. I'm not. This is a college level class, and in college level classes, math classes, it's very unusual for them to give notes on those tests. Practically unheard of. So here you go. Limit of sine x over x as x approaches 0 is 1. The proof of this can be found using something called the squeeze theorem. When our textbooks come in, I can show you a diagram and how it uses the squeeze theorem and stuff like that. But for right now, if you are okay, I'll tell you, you take my word for it. Okay? Two special trig limits. Limit of 1 minus cosine x over x as x approaches 0 is also equal to, well, that's equal to 0, the other one's equal to 1. So, well, that's not too bad. You might need extra paper for this. I don't know. We'll find out. Okay. Let's deal with, well, maybe we should just look at all these problems all together. What kind of stuff do we have? We have, some piecewise functions. There we go. Got some piecewise functions that we'll need to take the limits of. We've got some rational functions. We have some fractions of fractions, and some complex fractions. I'll show you how to do that here in a second. Yep.
Oh, I think it was 11. Yeah, that one.
You want to talk about one of those?
Mm-hmm.
Yeah, we will. And then these last four right down here, hey, look, those radical ones, you have to use the rationalized method on. Okay? Yeah, okay, sure, let's look at number 11. You'll probably need to do this problem on a separate sheet of paper. Just because the fractions of fractions get a little, I mean, they just take up space. It's not necessarily like a ton of steps. But essentially what we're going to be doing here is turning this one thing into a singular fraction. These are all sort of, what's the term, prepared for you in such a way that you can solve them very simply and using sort of the same mechanism. They're sort of like rigged up in advance, okay? They're like reverse engineered, so to speak. But that's not the problem. Anyway, you might say, I just want to plug in, do direct substitution. In your mentally, if you do that, however, you'll see you plug in -2. Immediately right here, you're going to get a 2 minus 2, which is going to be a 0 in this denominator. So it doesn't work, okay? So with problems like this that are complex fractions or fractions of fractions, the way to solve these without a calculator, without graphs and tools, is just to turn it into one fraction. Okay? So simplify everything. All right. What I'm going to do here is I want to turn this denominator, I want to combine these terms. Okay? Well, if you remember, fractions, adding and subtracting, you can't add and subtract fractions with unlike denominators. So what we're going to do is we're going to find a common denominator between 1 over 2 plus x and 1 over 2. So the solution for that is to multiply this term by 2 over 2, and to multiply this term by 2 plus x over 2 plus x. So that then my numerator is still x, in my denominator I have 2 divided by. Now here's where your life can actually be kind of simple. Don't distribute when you're doing these denominators. Just leave it as is. Say 2 times 2 plus x. And then minus, then I have 2 plus x over here, and this is 2 times 2 plus x. So I have x divided by, and now I can actually combine these. This is 2. Now I'm going to do this at the same time. I'm distributing that minus sign right there. So 2 minus 2 minus x all over 2 times 2 plus x. Rigel, do you see why I'm putting a minus 2 and a minus x? Because there's that minus sign right there. So here's my big fraction bar. So I have x, big fraction bar. 2 minus 2 is, yes?
Those are plus x.
Okay. This minus sign that's out in front applies to both of these terms.
Yeah.
Okay, so it's minus all of this.
Yeah.
So when I distribute that minus sign,
Oh, you're distributing the minus.
distributing the minus 1 because I can't just write minus 2 and then a plus x because that's not, it's literally, it's minus the quantity 2 plus x. So if I do minus 2, then I have the minus x right there. So then the denominator I have x divided by 2 times 2 plus x. And so I have a fraction with another fraction, and so I'll turn this fraction division into fraction multiplication. So instead of saying this divided by this, I'll say that the numerator times, flip it, reciprocal of the denominator. 2 times 2 plus x all over negative x. Notice I have an x multiplier in the numerator and x multiplier in the denominator. So those cancel, reduce to 1, and I just have negative 2 times 2 plus x. Believe it or not, this expression right here is algebraically equivalent to that mess up there. Say, I don't believe you. Well, we just did it. So, instead of saying the limit of blah, or the limit as x approaches -2 of blah, I'm going to say the limit as x approaches -2 of blee, which is over here, -2 times 2 plus x. It's the same exact problem. And now we can do direct substitution. So that's going to be -2 times 2 plus -2. And oddly enough, 2 plus -2 is 0, 0 times -2. We get 0 as an answer. Roger, ask me a question.
You kind of lost me whenever you did 2 and 2 plus x in parentheses. Did you move?
Like how I went from here to here?
Yeah.
Okay. There is a principle of mathematics, and that is if you have a big fraction, like a divided by b over c, something divided by something else is equivalent to the numerator times the reciprocal of the denominator.
Right.
So this is the big numerator. So like, if the big problem, numerator x times the reciprocal.
Oh, you just flipped it. Okay.
Just flipped it. Do you remember in junior high when you did this? You had 3/4 divided by 5/6. You then did 3/4 times 6 over 5. That's what it is. Division by a fraction is the same thing as multiplying by its reciprocal. And you also caught the minus distribution right there, right? Yep. Harley, what about you? Question. You can do that on your own? James, what about you?
I think I got it.
Okay. Believe it or not, problem of calculus is not calculus. It's algebra. Yes.
What happens if the fraction is on the numerator?
Yeah.
Like number 12.
Same kind of thing. Just combine like terms. I mean, like.
So would you have to like flip it for the reciprocal though?
So you're gonna multiply this by 3 and multiply this, or 3 over 3 and multiply this by -3 plus x over -3 plus x, right? In the process of that, inevitably, you're gonna get something that's gonna be like a over b divided by x. You're gonna combine this whole thing into one fraction.
Yeah.
And then you're gonna say that's a over b times 1 over x.
Okay.
Rigel and Harley, let me say that so y'all get that. Like on number 12, you'll combine these things, okay, by, to find a common denominator, like you multiply this one by 3 over 3, and you multiply this one by -3 plus x over -3 plus x, right? Okay? You'll do that, get the common denominator, combine it, and so the idea is in that numerator you'll end up with some fraction, and the denominator will still be x. Your next step would then be to write that numerator as is, a over b, times the reciprocal, 1 over x. And if you're lucky, there's going to be something in that numerator which has like an x in it, which then is going to be able to cancel those out, which is exactly what will happen. It's not really working without clearing that. Okay, good question, Ivan. I think you can see some similarities there with those other problems. We talked about the factoring types. That should not be an issue. Let's go ahead and look at these piecewise functions, shall we? How can we solve a piecewise function without doing a graph, right? Well, the answer is, think about what it looks like as a graph. Okay? Now, Rigel, tell me this. What does this kind of a thing look like? What is negative 2x plus 1? What kind of a graph is that?
Linear.
It's a linear, exactly right. It's a line. We know that's got a y-intercept of 1 and a slope of negative 2, right? So if I were, and it's going to be that way all the way up until 3, okay? So it's going to look something kind of like that, right? James, what does this graph look like? X squared plus 2x minus 2.
It's going to be a parabola.
It's going to be a parabola, absolutely. And it's going to look that way every place after 3, right? So maybe it looks like, I mean, maybe the parabola would come down, maybe it's going to look like that. Or maybe it's going to look like this. Or maybe it would look like, oh, it's negative, so it's going to be upside down. Maybe it's going to look like that, or maybe it would look like that, or maybe it would look, I don't know. If it looks like this or like this, then the limit as x approaches 3 clearly would not exist, right? However, if it looks like this, then the limit does exist. You see what I'm saying? So like, all right, how do I figure out what the situation is, whether or not this limit exists? And the answer is by looking at the limit as it approaches 3 from the left, and also looking at the limit as it approaches 3 from the right. And see what's that relationship. Does the limit of this function as x approaches 3 from the left approach the same number as it does from the right? Does that make sense? Okay, so how do we do that with this? Real simple. This is a well-behaved function. This is a well-behaved function, right? So we just do direct substitution on this side, and we do direct substitution on this side. And we see if they're both approaching the same value. In this case, we would have negative 2 times 3 plus 1 versus negative 3 squared plus 2 times 3 minus 2. And we're out of time.
Does that exist? Right?
Exactly, yes. Because that would be like one of these situations.
Okay.
But if they're both approaching the same number, then the limit does exist, and it's that number.
Okay.
So they look really intimidating, but those are actually pretty straightforward.
Would the first one be D&E?
This is negative 6 plus 1, so that's negative 5.
Oh wait, oh yeah, that's the first one. That's the first one.
And then this one's negative 9 plus 6 minus 2.
Oh, it's a negative 9.
Right, because it's negative outside the parentheses. So negative 9 plus 6 is
Negative 3.
negative 3 minus 2 is negative 5. So it looks like they both approach negative 5, in which case my graph should have been shifted way down here, but that's okay. They both approach negative 5. The limit does exist, and it's negative 5.
Second.
I'll take it from you.
0.
Thank you.
This is 24
Um,
and this is 9.
I'm going to give you 2 days on this, so try maybe 1 or 2 of each one of these problems, okay? And in the first couple minutes of class, we'll look and see if you have any questions on those. So the whole thing isn't due tomorrow, but try 1 or 2 of each variation. You can close it, turn it off. Thanks for watching.